Welcome to this test review for trig functions. Before I get started, just an important fact. There's three things I'm going to write down. You need these three things as a minimum for order for you to be successful tomorrow when you take this test. You got to be able to remember. You have to be able to understand. And finally, you need to be able to apply. You need these three as a minimum in order for you to say that you feel ready to take tomorrow's test. Now, in order to achieve, one of the things I love about this is that in order to achieve, you don't get these three things just by watching this video. This video is just as a tool to help you in each of these steps. What you're going to have to do is sometimes go ahead, rewrite the problem on a different sheet, and see if you could test yourself on these three things. Remember, only you could see if you're ready for this test. Great, let's go ahead and get started. A couple of things. First question, we're going to be simplifying. And in simplifying, one of the things we're going to do is use a lot of identity properties in order to get the solution. So when I look at like 1 cosecant x, the solution to this is just, now you could find this in your identity sheet, or you could convert it. And then from there, this becomes 1 times, we reciprocate the denominator. So it just becomes sine x. That'll be the solution in that one. But actually, if you would have looked at your identity sheet, it just would have said that this is your solution, sine x. Now let's move on to the next one. Now this next one right here, this part, let me erase this top one then. So just make sure we leave some space. On this next one, we have the benefit that the denominator is actually an identity property. It's sine square x. And this is sine x times cosine x. Now, there's 2 sine x's in the bottom. If you want, let me write that out for you to make it very clear, especially for those. Sometimes people see the square. You understand it when they see x's, but not so much in sine. This just really means that we have sine x times sine x. It makes it very clear that those cancel out, and your solution at the end comes out being cotangent x for question 2. All right, lovely. Let's go ahead and move on to question 3. Question 3 is that this is 1 plus, this is the same thing as tangent square x, and then this is equal to cosecant square x. So that'll be the solution to that one. All right, lovely. Let's move 4. 4 is that this tangent square x plus 1 is the same thing as cosecant square x, and this is the square root of that. This cancels out. So the solution from there just comes out being cosecant x. Okay, great. Love the fact that this is not very intense, so it should be fairly easy to comprehend. Now, from this one, this becomes cosine square x. These cancel out. Cosine x is the solution. Now, for question number 6, you have cosine and secant. Actually, this is these two do cancel out because we have the benefit. Remember, anytime you're working with some of these, it's easy. It's the best thing to do, or a good strategy to try. Change everything to sine and cosines. Cancels out, becomes 1. Lovely. Let's move on to the next one. Now, the next one is just an identity property. This is just equals 1. So once we discover that, that's it for this one. Now, for this one right here, this is actually the same thing as 1 minus sine square x. So once you make that connection, you go ahead and call it cosine square x, and that'll be your solution for that one. Okay, great. Let's move on to the next one. Now for question 9, as a tangent and cosine, we're going to go ahead and convert this to its equivalent to see if we could go ahead and find the relationship that exists between both. That cancels out with that, so the solution is just sine x for the question 9. Lovely. Let's move on to question 10. Okay, question 10, just cosine square x minus 1. Now, this is not sine square x. That's actually maybe the first thing you're thinking about because you're seeing. You do have the power to do things, but for the most part, nothing's going to change. The only thing that this can convert to is possibly a negative sine square x. It's the only thing I could see this happening. And the way we do this, let me go ahead and see. The thing is that the identity on this one is 1 minus cosine square x. So it's kind of easy. It's like, oh, if I could reverse these signs, I could make it look like this. And I love to do that for you. But in order to do so, you have to pull out like a -1. That becomes a negative cosine x. That becomes a +1. So when you rewrite this, now it fits the format that's correct to change. So if anything, it becomes negative sine square x afterwards. But that's pretty much all you could do with it. Now, for question number 6, since you have 6 sine, the solution is itself. You could try to convert it and make it into something else like cosecant secants, but it's still going to leave you with 2 terms. There's really no simplification there. This one, the only thing you could do, question 12, to simplify, is just pull out a 4. Pull out the 4, and we have the benefit that this is 1 minus 2 sine square x. And you can't do anything else with it because, unfortunately, if you try to pull out the 2, it changes the whole dynamics of it. You really can't make it into a cosine. Well, you could, I guess, in one part of it, but it doesn't. It's just going to be sines here. It's just to be sine with numbers. It's not going to do anything else. Okay. All right, lovely. Let's go ahead and move on to question 13. Okay, now with question 13, we have the benefit that in seeing that this one with tangent on top, one of the things that I'm going to do is I'm going to go ahead and convert this to secant square x minus 1 over secant x. Now, most of you that are watching this video come with a good, healthy benefit in understanding difference of squares. That means, but you're used to seeing it in this kind of fashion, x squared minus 1. And you're very smart in knowing that if you do x plus 1, x minus 1, when you factor it out, that it produces that solution. Well, the same is true of secant square x minus 1. So I'm going to go ahead and make this secant x plus 1, secant x minus 1, and then the bottom is secant x plus 1, and then we have the benefit of secants canceling out, the 1 and the -1 cancel out. Secant x is your solution at the final completion of that. All right, great. Let's look at this next one. Now, one of the things I'm going to do for question 14 is I'm going to go through the a few processes. I do want to change everything to sine to cosine, but first I'm going to take advantage in the idea that secant square x is actually tangent square x. I'm going to take advantage of that first, and then so this makes it over secant square x. And then let's explore the relationship that exists between the two fractions in numerator and denominator. Tangent, this is equivalent to sine square x. And basically, we're going to take the strategy of making everything to sine and cosines. Sine square x over cosine square x. And this is 1 over cosine square x. Now this makes it sine square x over cosine square x. We're going to multiply by cosine square x. And once we do that, we discover that the cosines cancels. Now remember, I did reciprocate this denominator, but the final solution is that this just becomes sine square x. All right, lovely. Let's go ahead and work on question 15, the last question on here. Now with question 15, we're going to go ahead and take the strategy of changing everything over to sines and cosines. So this is 1 over sine x over sine x minus cotangent, which is cosine x over sine x over sine x times cosine x. And what I'm going to do from here is I'm going to simplify each portion. Let me extend this. This right here, when I go ahead and I take the numerator and go through the process of dividing by multiplying by the reciprocal of the denominator, actually the other way around, sorry. I have to take the reciprocal, which means we switch numerators and denominators. We discovered that that becomes sine square x on that side. On this side, I'm going to take cosine x times divided by sine x, and multiply by cosine x over sine x. And one of the things we discover is that this whole thing becomes 1 over sine square x minus cosine square x over sine square x. The thing that I love about it is that we get a common denominator, and our result then could be written in, we have the benefit of writing the numerator underneath one fraction, and then 1 minus cosine square x is sine square x over sine square x. So we have the benefit that this just becomes 1 as a solution. Okay, great. All right, so that completes page 1. Now page 2 is going to do something that is slightly different that we haven't really done much in class, but because of the complexity of the problem, it does involve the use of using both sides of the equation. Not very common in proofs, but I think what they want to do is see if you have the manipulation skills. So like with question A and verification one of the things I'm going to do is that I don't like having denominators, especially when you have on the right side, you only have one numerator, no denominator, or the denominator is 1. So what I'm going to do is I'm going to multiply this by 1 times tangent x, and this is going to give me the power to cancel out on this side, but I got to make sure I multiply by 1 tangent x on this side. Now since cosecant, what I'm going to do next is I'm going to make it into sines and cosines, because since I'm going to be distributing, I would love to see how they interact. So this is sine x over cosine x. All right, so let's go ahead and quickly be able to distribute. This is going to be 1 over sine x. And then over here, we discovered that actually the sines cancel out and leave 1 over cosine x. Now that actually equals the same thing on the left, because left is really 1 over sine x over cosine x. But before I do that, I'll leave the reciprocal form names of it, secant x plus cosecant x, and I'll just switch out the right. Secant x plus cosecant x is equal to secant x plus cosecant x. I'm sorry, this one should have been cosecant x. The other one should have been secant x. There we go. Solved. All right, secant x. All right, and we have the benefit that these cancel out right here. We could subtract secant x on this side, subtract it on this side. And once we discover that that cancels, it leaves me with my proof that cosecant is equal to cosecant. Now, I'm imagining something similar is going to be done with B and C in this case. And we probably give it a try. But one of the things I want to do in this video, since I'm really short in time, I'll come back to these once we have time to get to them. I'd rather go to the ones in the back. These are more important. And solve each of these equations for you so we can have the benefit in seeing these first. Now, when we solve these, if anything, if this you leave alone, but you do solve for everything else, because we want to see what this is. So we're going to add radical 3, have the benefit that cancels, and then we're going to divide by 3, and we have the benefit that cancels. So really the question comes out being, when is tangent theta equal to radical 3 divided by 3? Specifically, just positive values. Some people sometimes get confused because they're wondering when they use positive and negative. That happens only if you take a square root. Then you have the effect that becomes positive and negative. So I'm going to bring up my unit circle. Now please remember, all these solutions are written in cosine, sine, and tangent. The thing that I love is that we only need to look at the tangent values. So I'm going to go ahead and start at 0. That's not it. Here's one solution, so there's 1. That's not a solution, that's not a solution. The other one's undefined. I should have brought that down, minimize that. not a solution, not a solution, not a solution for tangent, not a solution. Ah, here's the one solution. 7 pi over 6. Not there, not undefined, not this, not this. So one of the things that we discover is that pi over 6 and 7 pi over 6 are actually the two solutions. So what we do afterwards, we have the benefit that we're only working with theta. So we have the power just to write down the two solutions without any kind of modification. So there'll be the two solutions for that one. Now let's go ahead and work on question 18. Question 18, same thing, we're going to simplify. Minus 1, that cancels out, divide by 2, divide by 2. I'm going to go ahead and now find out when sine 2 theta is equal to negative 1/2. One thing to keep in mind, this 2 theta means I have 2 unit circles, which means that normally with theta I had 1 unit circle, but since I'm doubling it, multiplying everything by 2, it makes sense that I will jump to now an interval that will go up to 4 pi. So specifically, I'm going to be looking for solutions that go 2 unit circles. That's why the 2 theta that you see up there. And so let's look at the unit circle and kind of come up with the conclusion or find out where these solutions exist. Let me clean up my previous markings. Let's go ahead and find out where these solutions exist for this one. All right, so we're going to start with, we're looking for negative 1/2 cosine. So no, 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 yes. So that's a solution. No, 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 yes. That's a solution. No, 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 and no. So there's only these two places that happen the solution between 0 to 2 pi. Now from here, it's important to remember that any angle that goes past 2 pi, like this angle is no longer pi over 6, it's now 2 pi plus 1 pi over 6, which just comes out being 2 1/6 pi. And you could, if you need to convert it back to an improper fraction, which is important at times, 2 times 6 plus 1 means that this is really 13/6 pi. And we take this, multiply with this, add with the numerator. But we're really trying to find out, when I go here, the same solution exists in the same spot. So that means that this is really 2 2/3 pi as a solution too. And then I hit 3 pi. Then I come here and then I hit 2 4/3 pi. Remember, this is 3 pi. And then eventually I end up at 4 pi, and that's it. So I come up with these 4 solutions. Now, one of the things that I am going to do, because I'm going to have to kind of reconvert it, I will go through changing them from this format. 2 times 3 is 6, plus 4 is going to be that this is really 10 over 6 pi. And then this is 2 times 6 plus 2, so it's 8 over 6 pi. Which just reduces down to 4/3 pi. So that's true. 2 over 6. Yeah, it does reduce to 4/3 pi. Oh. Oh, actually, no. Let me clarify something. I'm doing that wrong. This remains as 3 when you do this process. Same thing here. This remains as 3, so it does not reduce. And the same thing what I said over here, 2 times 6 add, but you keep this. Actually, no, you do keep the 6 in that one. There is a 6. I think the 6 is what confused me for the other ones. But for the most part, that would be these would be the solutions. But this is specifically what I'm looking at these 4 solutions. So I'm going to pull with me 2 pi 3 go back to this. So one of the things I discovered is in the 2 unit circles, I discovered 2 pi divided by 3. I also discovered 4 pi divided by 3. And then we also discovered 8 pi divided by 3 and 10 pi divided by 3. Now, there's a necessity that occurs. If I call any of these as solutions, and I try to put it back specifically right here, I go past my intervals. So like, let's say I take 10, 2 times, I call this sine 2 times 10 thirds pi. One of the things that happens is that this becomes 20 thirds pi, and this is roughly equivalent to 6 pi, 6 and 1/3 pi. Way past this 4 pi interval. So I need to convert my solutions so when they go as an input, they stay in the interval. And the way I do that is I solve for theta. So I divide by 2. Now you can think about these as dividing by 2. I find it easier to think about it as multiplying by 1/2, which is the same thing as division of 2. 1/2, 1/2, 1/2. We have the benefit of that cancels, so the solutions actually just come out being 2 pi over 6, 4 pi over 6, and all these could be reduced. 8, 6 pi, and 10 pi over 6. Since all of them be reduced, I'll go ahead and reduce them. Pi over 3, 2 pi over 3, 4/3 pi, and finally 5/3 pi. Lovely. And that'll be the solution for that one. All right, let's go ahead and look at the next one. Now next one has a reciprocal value to it. So one of the things we're going to do to discover this solution is we still solve. We still divide by 3, so we add 4 to both sides. And then we still take the square root, which creates a plus or minus, and it cancels that out. But specifically, this is what I'm going to end up with. And let me erase some of this other stuff over here so as to no longer take our confusion or space at all with this. This comes out being cosecant theta plus or minus. I'm going to separate the radicals because you have the power to separate the radicals when they're like this. And this simplifies even some more to it becomes plus or minus 2 over radical 3. Now, a lot of people sometimes when they get to the simplification, they want to jump right ahead and rationalize the radical 3 because it's in the denominator. Before you do any more solving, it's very important.
Good morning, teachers. Sorry for the interruption.
Let me pause this. All right, so we're here at the step where once you get to the step, go ahead and make this 1 over sine theta, make it its reciprocal equivalent, and then make it plus or minus 2 radical 3. Now there's a property in where you could think about it as cross multiplication, but one of the things that happens is that you're able to switch numerator and denominator in space as long as you keep both of them the same. And you could prove it through cross multiplication. So I'm switching numerator and denominator, but also on both sides of the equation. So we have this as a solution. So we just need to find out where this happens in the unit circle. So let's bring up the unit circle. Let me clean up from the last problem. Okay, and I'm looking at the sign values. I'm looking when it comes positive or negative square root of 3. No, no, yes, solution, no, yes, solution, no, 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 yes, solution, no, yes, solution, no, and no, and no. So that means we have pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 as solutions. So when I come back here, all you need to write down is 2 pi over 3. Let me go back. I think I'm supposed to start with pi over 3. Yes. So I'm going to come back over here and just put it in order. Oh, it's not going to let me do that, so I'm going to erase pi over 3, 2 pi over 3. It wasn't, I think it was 4 pi over 3 and 5 pi over 3. And those are the 4 solutions that came up with question 19. All right, lovely. Let's go ahead and move on to question 20. All right, and with question 20, I'm going to go ahead and show you graphically what is happening because, see, it's already solved for. So I'm trying to find when cosine equals negative 1/2. But there's two things that's happening. First of all, this 1 theta by itself, like this, is 1 unit circle. You see the divided by 2? It means we're cutting the unit circle in half and discarding, only using half the unit circle. In half. Okay, so that's the first thing we're going to do. We're going to cut the unit circle in half. And then this means that instead of starting at 0, we're going to add pi over 3. We're going to do a phase shift. I'm going to go ahead and actually move everything by pi over 3. Let me go ahead and erase this and show you graphical solution, then I'll show you the algebraic solution to doing it. All right, so let me go ahead and erase this. And first of all, the first thing I'm going to do, I'm going to cut the unit circle in half. So here's my half cut. That means none at the bottom counts, just the top. But then we're going to do a phase shift, so I'm starting at 0. I'm going to start at pi over 3. And pi, we're going to add pi over 3 too. So a new line forms, a new half the circle forms that goes in this direction here. And the thing that we discard all the solutions that exist pass over here. So we have the benefit of seeing exactly only where the solutions exist. Now let me show you the same thing in graphical terms. We're going to come up with the same solutions. In graphical terms, we are going to go ahead in algebraic terms, better put. Start with the default unit circle that goes from 0 to 2 pi. I'm going to cut it in half. So we have the benefit that that cancels. Makes the pi, the one we're looking at, that becomes 0. But then we're going to also be adding pi over 3. So when I add pi over 3, this becomes pi over 3. This is a variable at the middle, so now this last part, let me go ahead and fix this a little bit more. So it kind of went down as an angle, and I kind of need that space. Pi plus pi over 3, this is what I'm doing. Pi plus pi over 3, which is 1/3 pi. I got to get a common denominator. So I'm going to make this 3 over 3 pi, which gives me the power then to make it 4 pi over 3. Or the addition is 4 pi over 3. So from this, I'm taking that my interval is going to go from pi over 3 to 4 pi over 3. That's my interval. And it's actually the one we came up with already. We go back to here. Here's pi over 3. Probably should have done that in a different color. Here is pi over 3. And here is 4 pi over 3. So it does fit an interval. Now let's go ahead and do one of the most important parts. Find out when it equals negative 1/2. No, no, yes, yes, no, 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 yes. So there's my solutions. 2 pi over divided by 3 and 4 pi over divided by 3. So we're going to come right over here and then write down my theta is equal to, actually this is wrong the way I wrote that because this is not 1 unit circle that I got those solutions. I got 2 pi over 3 and 4 pi over 3 specifically from taking half the unit circle and adding a phase shift, moving it by pi over 3. Erasing this other stuff over here. So what I'm going to do is that we're going to have to solve for theta for the same solutions as we've done before to get everything to fit once we put in these values. So one thing that I do love is when I subtract pi over 3, I discover that we have common denominators automatically. So there's nothing that needs to be done there. we still have our angle divided by 2. The first one comes out being pi over 3. Next one comes out being 3 pi over 3, which is really just pi. And the last thing to solve for is multiply by 2. So multiply by 2 and multiply by 2. Now when I do that, we have the benefit that cancels. My solutions only come out being 2 pi over 3 and 2 pi. And these are both my solutions to this one. Okay, great. So let's go ahead and work on the very last one on this back page. And one of the things we're going to do is we're going to go ahead and same thing with this one. This one's solved already. So the first thing I'm going to do is I'm going to go ahead and change secant so it's reciprocal. 4 unit circles minus pi. Actually, that should be a parentheses here, not a bracket. And I'm going to make this negative 1 over 1. Now, we're able to reciprocate these values. So when I make this cosine theta, and the reason why I make it the cosine, sine, or tangent, like I'm reciprocating, making it in those terms and going through the work, is because my unit circle has those 3 values. So unless I want to create special unit circles, now reciprocate this, it still comes out being negative 1. So I love that. There's not really a change there. Now the only thing that is going to happen is that we're going to go through 4 unit circles, which means that if I took my regular interval, we're going to have the effect that it's going to jump up to a new interval, which is going to go be 8 pi. And then we're going to subtract pi. So one of the things that's going to happen is that we're going to start a negative pi here, because remember 4 times 0 is just 0, but minus pi means negative pi. We're going to go between here minus pi, and this is going to be 8 pi minus pi, so 8 pi minus pi is 7 pi. So I'm guaranteed to go between the interval negative pi and 7 pi in my unit circle. That's the interval I'm going to be looking at. So let's bring up the unit circle and find out where the solutions are going to want to occur in those terms. Let's see if this does it a little bit easier. No. I was trying to see if I could maybe erase it a bit faster. I had to practice that technique. So that if you move it all in the circle and look in the middle, it's supposed to erase. All right, let's go ahead and discover now. And the only thing is that we're going to start at negative pi. This is 0. Anything this direction is negative. Everything we've encountered so far has been positive. So I'm going to go specifically negative pi. And at negative pi, it's negative 1. See the solution? So I count negative pi. And this is back at 0. I count pi. 2 pi, count 3 pi. Count 5 pi. Because we get to 4 pi, 5 pi, 6 pi, and I count 7 pi. And I stop there because I don't go past 7 pi. So these are my solutions that occur in this, like when I write down, one of the things I discover is that 4 unit circles minus a pi produces the solutions negative pi, pi, 3 pi, 5 pi, and 7 pi. So what we're going to do from here is that the first thing I'm going to do is I'm going to solve for theta. So we're going to add pi, add pi, add pi, add pi, add pi, and I discovered that my 4 unit circles, and we'll have 0, 2 pi, 4 pi, 6 pi, 8 pi. We're going to divide by 4. That cancels out. My angle then is going to be 0, That reduces pi divided by 2, pi, 3 halves pi, and 2 pi. So these are all my solutions for this. Okay, great. All right, listen, I wish you the best of luck in the exam, and please take the time, rewrite the question, see if you can do it yourself without any help. If you can't seem to get it, relook at the video, write it down again, and then retry again. Your goal should be that you should be able to do it without assistance, without looking at any notes, be able to recreate everything you just created. Good luck tomorrow. Thank you for watching.